Hi, I'm Bilal Ahmed. Today I'll be presenting our work on scalable formal verification for NOC designs using a technique called path decomposition. Here's the plan for today. I'll start with the motivation, why NOC verification is particularly hard to scale. Then I'll give a quick overview of what NOCs are and the key properties we care about from a verification perspective. After that, I'll walk through our formal verification strategy, including the abstractions we apply. I'll then introduce path decomposition, which is the core idea behind making this approach scalable. I'll also share a few real bugs that we uncovered using this technique. And finally, I'll wrap up with the results and benefits of our approach. Network on chips, or NOCs, are a key communication IP in modern SoCs. As SoCs scale to tens or hundreds of processing elements, NOCs provide the scalability, performance, and modularity that traditional bus-based interconnects cannot sustain. As a result, their adoption has increased significantly in large-scale and heterogeneous SoCs. From a verification standpoint, the scale creates challenges. Conventional simulation struggles to prove properties such as deadlock and live log freedom, since these issues often appear only in rare case scenarios. Formal verification can provide exhaustive guarantees, but conventional approaches fail to scale beyond small NOC instances. As a result, a practical and scalable formal sign-off methodology for large NOCs is still missing. Network on chips provides scalable, high bandwidth communication for multi-core and heterogeneous SoCs. Communication is distributed across a network of routers rather than a centralized interconnect. Routers are typically arranged in topologies such as mesh or ring, with each router connected to a processing element. The NOC is responsible for moving packets between processing elements through this router network. As the figure shows, a NOC is arranged in a 4x4 mesh of routers connected with their respective processing elements. Each router includes routing decoders, arbitration logic, FIFOs, and multiple communication channels. The interaction of these components across the network leads to complex behaviors that make verification challenging. When verifying a network on chip, the focus goes beyond individual routers or signals. The objective is to ensure correct behavior of the entire network under all traffic conditions. NOC properties describe both functional correctness and forward progress across the system, just like the deadlock freedom. The network must never reach a circular dependency where packets cannot advance. Live log freedom, where packets must not circulate indefinitely without delivery. Starvation freedom, every packet must progress forward and eventually evacuate the NOC. Data integrity, where every packet arrives at their correct destination uncorrupted and in order. Liveness injection, the system must make progress under continuous injection. These properties are inherently end-to-end and become increasingly challenging to verify as the network scales. This slide summarizes our formal verification strategy. We start with compositional reasoning, where instead of verifying the entire NOC monolithically, we verify individual building blocks in isolation, such as the decoder, the router, arbiter, and the FIFOs. Once these proofs are established, they are assumed as guarantees at the next hierarchy level to verify router level properties, including flow control, packet forwarding, and interface compliance. Next, we move to the end-to-end verification, where we try to prove the NOC properties as we discussed in the last slide. Here we focus on packet movement through the network rather than internal microarchitecture details. To enable this, we use a packet tracker methodology, which allows us to follow a representative packet from injection to delivery and ensure packet integrity and ordering during the path. We further control complexity using parameter reduction, scaling down FIFOs and channel parameters. Case splitting is used to separate each possible path from each other to create mutually exclusive scenarios that can be verified independently. We also applied packet coloring, which helps us distinguish different packets and reason about interference and ordering without tracking every packet explicitly. Finally, we introduce path decomposition to scale our verification effort. We begin with compositional reasoning. Instead of verifying the node design as a single monolithic part, we decompose into independently verifiable components, such as routers, arbiters, FIFOs, and channels. As can be seen in the block diagram, for each component, we first prove local correctness properties in isolation. For all router submodules, as can be seen that every submodule has an SVA attached to it, and that proves that submodule independently. After this, we assume these local guarantees to help prove router itself. Once the router is proven, we assume router properties as guarantees to prove network level properties. To prove network level packet integrity and ordering, we used an end-to-end packet tracker methodology inspired from the smart tracker introduced by Imagination Technologies. Rather than modeling all packets explicitly, we symbolically track a representative packet, ensuring that its integrity and ordering are preserved as it moves from the source to the destination. We also use packet coloring to encode the packet's source and destination information, which allows us to reason about routing correctness and interference without tracking even every packet in the network. To further control complexity, we apply case splitting, where each possible path is analyzed independently, allowing the formal tool to focus on one scenario at a time. In this example of a 4 by 4 mesh, we have 240 unique possible source destination paths. We split all these paths, and for each path we use packet tracker methodology to prove data integrity and ordering for every path. However, even with these abstractions, we were only able to verify paths of 2 to 3 hops, and the runtimes were already very significant. Longer paths still continue to struggle to converge, which motivates the introduction of the path decomposition technique that we will introduce. Despite using packet trackers on every individual path, along with router level guarantees, we hit a significant bottleneck. We simply couldn't get longer paths to converge. As those paths grew, the state space of the design exploded. We effectively reached a scalability wall where proofs for anything over 3 hops wouldn't converge, even after running for weeks. To put the gravity of this into perspective, when we mathematically extrapolated those proof times, the data showed that a single 6 hop proof would take nearly 2 years to complete. It was clear at this point that our current approach had reached its absolute limit and we needed a fundamental change in strategy. To overcome the scalability wall, we developed a new approach, the path decomposition technique. We begin with building a predictive routing model in Python. The core strategy here is a classic divide and conquer algorithm. Instead of attempting to verify a massive end-to-end path as a single path, we break those longer paths down into smaller, manageable subpaths. However, simple decomposition is not enough. We have to ensure the individual proofs still represent a valid total path. To guarantee correctness, we implement overlapping subpaths by ensuring that the tail of one subpath perfectly matches the head of the next one. We maintain the chain of trust across the entire route without the exponential overhead. You can see that the mathematical impact of this shift in our approximation formula. The time for a k hop path, for example, a 6 hop path, the time for that 6 hop path is 6 divided by 2. 2 is the path subpath that we are taking we are dividing our subpath into two hop path. So 6 by 2 into time taken by a two hop path. So this is how we approximate a exponentially growing problem into a almost linear problem. With this, we have replaced years of computation with a process that scales predictably and efficiently as the network grows. So let's see an example where we use this path decomposition technique to scale a four hop path into two hop subpaths. So here we have a source router is R0 and the destination router is R7. So the path that we predicted is in this specific routing, the path would be R0 to R1 to R2 to R3 to R7. So we know this is a four hop path, and generally in the using the just the packet tracker technique, it would take up to weeks of computation power. So what we do using path decomposition is we break this whole problem into two shorter problems. So what we do is we use the first we verify the R0 to R2. So what we are tracking, we're tracking the packet from R0 to R7, but we are tracking that same packet at R2. We see that the packet has been injected at R0. It traverses from R1 to R2. We see that the packet we see at R2 is the packet destined for R7. So we verify, okay, the packet destined for R7, uh, we can see that packet at R2. So we this output packet tracker shows us, okay, that the packet has arrived. So we verify this path in 10 minutes. And we can say, okay, this path from R0 to R2 has been verified for a packet destined to reach R7. Then what we do next is we verify the next route from R2 to R7. This is the part where we told you before that the overlapping technique that the packet was has reached has left out of the router 2, but we verify it from entering into R2 in the next step. So the packet tracker input packet tracker sits at the entry point of R2. We see, okay, the packet destined for R7 has entered R2, and that the packet is traversing through R3 and has reached R7, the output. So this is how we verify, okay, the packet destined from started from router 0 destined to R7 has started from R2 and has reached R7. So this is how we proved this first subpath and the second subpath. And now we can assume, okay, these both routes are true, and then we can prove this whole path, and it will be proven in couple of minutes rather than couple of weeks. This slide summarizes the key results of our approach. Using path decomposition, we achieved complete end-to-end verification of all the 240 source destination pairs in a 4x4 mesh NOC from base jump library. And this was done within 24 hours, something that is not feasible with conventional formal analysis. All liveness properties, including deadlock freedom and starvation freedom, successfully converged within 72 hours. Importantly, these experiments were run on a standard workstation with an Intel Core i5 processor and 16 gigabytes of RAM, demonstrating that the approach does not require high compute resources. Finally, after excluding dead code, we achieved formal coverage closure across multiple mesh configurations and different vendors, ensuring that all relevant behaviors were exhaustively checked as shown in the table below. Exhaustive formal verification revealed corner case bugs in the NOC design that were missed by simulation under the tested configurations. Some of the observations were made on mutation analysis. The first class of issues involved a packet dropping bug. Here, improper synchronization between FIFO readiness and output valid signal caused packets to be dequeued but never forwarded, resulted in silent packet loss. The second class involved an arbitration bug where a rare overlap between route computation and buffer arbitration led to incorrect output port selection and, in some cases, packet misrouting. In both cases, formal counterexamples precisely identified the coordinates and provided cycle-accurate traces, enabling targeted fixes in flow control and arbitration logic. This slide highlights the key benefits of our approach. Firstly, it enables scalable formal sign-off for large nodes by directly addressing the state space explosion problem that limits traditional system-level formal verification. By applying path decomposition, we transform what is typically an exponential verification problem into a near linear scaling problem, making deeper paths and large networks practically verifiable. As a result, we are able to provide complete end-to-end guarantees, including deadlock freedom, live log freedom, and packet integrity across the network. The plot on the right illustrates this effect. Without decomposition, proof runtime grows super exponentially with the number of hops, while with decomposition, runtimes remain bounded and almost linear. Overall, we observed up to 10 raised to power 5 times improvement in the runtimes, and with this we achieved 99% formal coverage. Finally, I'll briefly outline directions for future work. First, we plan to extend the framework to additional NOC topologies beyond regular mesh and torus networks. We also aim to support adaptive and non-deterministic routing algorithms, which introduce additional verification challenges due to increased behavioral complexity. Another important direction is to automate assumption generation and abstraction refinement, improving usability and reducing manual effort for verification engineers. Finally, we intend to apply this methodology to heterogeneous and hierarchical NOC architectures, bringing scalable formal verification closer to real world SOC designs. Thank you.